Hello everyone, and welcome back to another midterm question. In this tutorial, we're going to do the 2013 midterm question 2. So just by looking at the question, it should scream particle equilibrium to you guys. It's kind of not really a secret that particle equilibrium will be on the midterm. Very, very common topic, and it's usually always 3D, because 3D really tests your knowledge on knowing everything about particle equilibrium, as well as 3D vectors. So let's just go through real quick, see what the question's asking, and then we'll go from there. So the question says a flower pot is suspended by 3 cables. So very, very basic, 3 cables, because as you guys remember, usually you have 3 unknowns, 3 equations. Makes sense. Joined by a ring at point A, as shown in figure 2. The ring at A is on the y-axis, and point B is on the YZ plane. And then finally, use gravity equals 9.81 meters per second squared in your calculations. So I like that because a lot of students have asked me, what do I use for gravity? Well, it'll usually say what you should use for gravity. We want to keep all your answers consistent, stuff like that. But what's kind of a little bit interesting is it doesn't give you a mass right away. So you're thinking, okay, what may I use that gravity for? Well, let's read part A, see if it gives you a mass, and you guys can look. It does. So it says, if the flower pot has a mass of 50 kilograms, determine the magnitude of the force in each of the 3 cables and include an appropriate free body diagram in your solution. So this is interesting because even if it didn't ask for a free body diagram, you're dealing with equilibrium. So even if it didn't ask, you should always have a free body diagram when you're dealing with equilibrium. Now, it's kind of hard in 3D to make it nice, but this is what I usually do, is I find the point at which everything kind of acts on. If we look at this, that's going to be that point A right there. All of the 3 cables go there. That's where the flower pot is hanging. So what I'm going to do is I'm just going to draw a point, and this is going to be my point A, my particle, if you will, in the particle equilibrium. And as we can see, we have 3 forces. So I'm just going to draw all the forces there. So I'm going to have one that kind of comes out like this. And remember, it won't be exactly to scale, and that's fine. We're not looking for perfect free body diagrams. We just want it to be more or less legible. We can read it and we can kind of understand and say, okay, well, it includes all the things that we want and what we're looking for. So here's the 3 forces due to the cable. But then, of course, we have a force going downwards because of the mass of the flower pot. So we have 4 cables here. In the end, one of them is just equal to the weight of the flower pot, which is going to be mass times gravity. And we can substitute this in because we know that the mass is 50. Gravity, it says to use 9.81. So the weight of the flower pot is going to be 490.5, and this will be in newtons. All right, so that part was so easy, but let's see how the rest goes. So the next thing we got to do is we got to label all these unknown forces. So if this is point A and we're going on the right side, this right here I'm going to put as F, A, and it goes to point B. And kind of moving along counterclockwise. At the top here we'll have F, A, C, and then at the side we have F, A, D. Now, although all of our forces are labeled, remember a free body diagram should also have some unknowns, or sorry, not the unknowns, some dimensions, something that we can use to solve for the components of these. So in this case, our best bet is that we have coordinate points. So if we look at point A, we know it's 0 in the x, it's 2 in the y, and 0 in the z direction. That is units of meters. For FAB, we know that it goes to the coordinate point, which is 0 in the x, 4 in the y, and 2 meters in the z. So I'm going to put this coordinate in. FAD, on the far side, we know is 1 in the x, 0 in the y, and then 2 in the z, in meters. And finally, we can throw in the last one, which is -1, 0, 2. So finding these coordinate points should be pretty easy, and they're probably pretty necessary in the free body diagram because then we can use it to start figuring everything out. Nice and easy. So this should be the free body diagram, but the last thing that you guys should have is just maybe somewhere in the corner here is you have to define your sense of positive directions. Because remember, a free body diagram, you can define your x and y axis however you like. So sometimes it's good to just let the marker know, or let me know, which way you're taking as positive x, y, and z. So that, just put it there, kind of show which direction's which. So if I were to look at FAD on my free body diagram, just by the look of the arrow, I don't know where it's going. This is why I'm saying it doesn't really matter if it's really to scale, but I have the coordinate points between the two, so I can easily determine which way it's going. So that's the important part, is I can solve everything using this free body diagram right now. So now we have to try and think, okay, well, particle equilibrium, well, that's equilibrium equations. You know, some of the forces in x, some of the forces in y, some of the forces in z. The only problem is we need the components. I have FAC, but I need that number in front of FAC, let's say 0.62 or something like that. How do I find those? And this one you have to remember that for 3D, to find those components, the best thing to do is finding the unit vectors of all of those forces, because the components of the unit vector, that's the conversion you need to go from your force to an x component or a y component, something like that. I know that kind of sounds a little funny, but let's go through the question and hopefully it'll make sense. So what I'm going to do is I'm going to put components. This is what I want to solve for. And I'm going to put unit vectors. Unit vectors. So let's just see really quick. There may be some tricks in here, because 3 unit vectors, that's a lot of work. So let's just find out what happens. Let's start on the very left, FAD. So for FAD, we know that the unit vector of FAD, so I'm just going to put UAD, we can find that if we find the position vector AD, and we divide that by the magnitude of FAD. Well, we can find the magnitude if we know the position vector. So the position vector, RAD, we know is going to be equal to the coordinates of A minus the coordinates of D. And that is completely incorrect. I want to see how many of you guys I caught. Remember, it's the opposite. And this was what will get a lot of students on the midterm. It'll be RD minus RA. So if we look up here, we have the coordinates of D. It's 1, 0, 2. So 1, 0, and 2. And we're going to subtract the coordinates of A, which are 0, 2, 0. 0, 2, 0. So we find that RAD is going to be equal to, and then I can put my squiggle brackets because it's going to be a position vector. And what we're going to find is equal to 1I minus 2 in the J, and then plus 2 in the K direction. And the squiggle brackets and the subunits of meters. Now, if we look up at the unit vector, we also require the magnitude of RAD. But that's very, very simple to solve if we have the actual vector. So RAD, we know it's going to be the square root of everything inside squared and added together. So we're going to go 1 squared plus 2 squared plus 2 squared again. And what we find is this is equal to 3 meters. So I'm just going to end that right there. So far so good. We're finding the unit vector. The only thing you guys will really notice right now is this. It's just tedious. Let's be honest. It's just tedious. It's not super hard to do this. It's just really, really tedious. So hopefully that there's some tricks for the next part so that it's not, we don't have to keep doing this. So UAD is equal to, in brackets, and we're just going to divide all those components by 3. So we're going to get 1/3 in the I direction minus 2/3 in the J direction, and then plus 2/3 in the K direction. And this will have units of nothing. Because remember, unit vectors, we're taking a unit of length, we're dividing it by a unit of length, they cancel, no units. So that's our unit vector right there. So we found 1. We got 2 more to go. So if we're going up here, okay, well, if we're continuing the circle, we're gonna go FAC. So right here, we can go FAC. And then we can go, oh, well, hold on a second. Let's look at just magnitudes for a second. Not directions, but just magnitudes. To go from A to D, what we just did, we had to go -2, or we're not even worried about the direction. We had to go 2 in the Y. Okay, well, that's the same thing we do to get to C. In the Z direction, we had to go 2 up to get to D. Oh, that's the same as C again. And if we look at the X direction, to get to point D, we had to go +1 in the X. But to get to C, we had to go -1. And then you start to realize, hey, those two are symmetric. Well, what does that mean? It means that the unit vectors are actually going to be the same. But the only difference is the direction that changes. In this case, it's the X direction. We just have to switch the sign. So, if we get UAD is that, we can easily find UAC as we just switch the sign for the one that changes. So remember, the only thing that changes between these two is the I direction. One goes in positive, one goes in negative. So we can go -1/3, so instead of +1/3 in the I, and the other two don't change. So we're going to have -2/3 in the J, and then +2/3 in the K. So really quickly, we're able to find that unit vector without even really doing any work. Saved us a lot of time, a lot of tedious calculations. So, and the reason why, this is symmetric. I see symmetric with FAD. All right, well, now we're done 2 out of 3. So we go up here, which one do we have left? Oh, FAB. And now FAB is a really special case because there is a trick to it. Oh, it's B. Sorry, it's not D. FAB. So there's a trick to this one. And the trick is it's actually a 2D case because it's in the ZY plane. It has no X component whatsoever. However, let's say you don't know that trick. Well, what do? Well, we find a unit vector. And we do the same thing that we did before. So we're going to want to find RAB, which goes from coordinates A to coordinates B. What we're going to do, if we find that out, is we see that it's going to be 0I plus 2J plus 2K. Subunits of meters. And what we can do is we're going to find the magnitude, RAB, which is equal to the square root of 2 squared plus 2 squared, which is equal to, 2 root 2. And the subunits of meters because it's a magnitude, it's a length still. So then what we can do is we can say that the unit vector of AB is going to be equal to all those components divided by 2 root 2, which we see just turns into 1 over root 2. So for this one, we put the squiggle brackets. Well, it's still going to be 0I and then plus 1 over root 2 in the J, and then plus 1 over root 2 in the K. Now, I said that there's a trick to this, so we can easily find it using our methods before, but was there a trick to this? Well, of course there was, because it's 2D, and I'll show you this right here. So this is what we had. We had a nice triangle. I'm not sure if you guys saw it, but we actually had a nice triangle. So we could have found these components like they were in 2D. So from here to here, this direction right here, that's going to be our F, A, B, and the Y. And then going up to the top, it's going to be F, A, B, in the Z direction. So we could have found these by just using trigonometry. So if we know this angle here, which is 45 degrees, we know that FABY is just going to be cosine of 45. And if we check this out right here, it's going to be cosine of 45. Well, what do you get when you do cosine of 45? You get 1 over root 2. And similarly for the other one, it'd be the sine of 45. What do you put when you get the sine of 45? Well, you get 1 over root 2 again. So the trick is knowing which plane it's in, because it has no x component. So that's the only thing you have to realize. It's in a plane. Okay, well, I can treat that as a 2D case, and I can use cosine and sine to solve for them really fast. And then the other one would just be 0 because it has no component in that plane. So now that we have our unit vectors for all those forces, we can go to what equilibrium is really about. And this is where a lot of marks will come in. If, say you get the final answer wrong and we're curious where you went wrong, this is what we're going to check. And that's your equilibrium equations. So remember, for 3D, for equilibrium and for a particle to be true, it cannot move in the x direction, or it cannot move with an acceleration in the x direction, in the y direction, or the z direction. Therefore, the sum of the forces in all those directions must be 0. So let's start off with sum of the forces in x is equal to 0. So what we do to create these equations is we go up and we take the components of the unit vectors for those. So if we go up to the top here, for UAD, we get the unit vector as 1/3 I. So for sum of the forces in x, we're going to go 1/3 of FAD. Then we're going to look up and okay, well, for AC, we have negative 1/3 in the I. So I'm going to go minus 1/3 FAC. And if we look at AB, there is no I component. So this is the end of it. And for equilibrium, it has to be equal to 0. And what I do to keep track later is I'm just going to put ... 1, meaning this is equation 1. So when I'm referencing it later, I can just put 1. I don't have to write the equation out all the way. So we're going to do this for all directions. So we're going to have sum of the forces in the y direction is also equal 0. So let's go up to the unit vector, see what we see. So for UAD, for the j component, we get negative 2/3. So negative 2/3 FAD. And I believe it's the exact same for FAC, which it is, negative 2/3. So minus 2/3 of FAC. And we look at AB, and this one does have a component for the j, and that's plus 1 over root 2. And this is FAB. And this one's equal to 0 as well. It's equilibrium. This should all equal 0. So ... equation 2. Now the final one, the sum of the forces in the z direction is equal to 0. Let's go all the way up to the top. Well, UAD, we have 2/3 for UAD and UAC. So we're going to put 2/3 of FAC, or FAD, I guess, but it doesn't matter, so they're going to be the same, plus 2/3 of FAD. And if we look up for AB, we got another plus 1 over root 2. And this is FAB. And now we have to be careful, because yes, we did the 3 cables, but remember, we also have this force right here, which I'm going to underline in purple, acting in that z direction. And it's acting downwards, so we have to go minus 490.5. Minus 490.5 is equal to 0. ... Equation 3. So, now that we have our 3 equations, we see that we have 3 unknowns. We can begin solving these. So looking at these equations, it's pretty obvious which equation is best to start with. That's going to be equation 1. So what I can do is I can move FAC to the other side. So I'm going to have 1/3 of FAD is equal to 1/3 of FAC. So from there, well, the 1/3s cancel on both sides, so we can conclude that FAD is exactly equal to FAC. Okay, well, that's actually very, very, very nice. Now I'm going to go ... This is equation 4. So now I can take this and substitute it into a new equation. So let's take equation 4 and substitute it into equation 2. So equation 2 is the sum of the forces in the y. And the reason why I'm picking this is mainly whatever equation has the constant in it. So in this case, it's equation 3 with the 490.5. That's usually the one you want to save to the very end when you're actually going to solve for a variable. So what I want to do is I want to get everything in that third equation in terms of one variable. So right now, the only variable I'm kind of missing is that FAB. But if I go into equation 2, I can very easily find it. So from equation 2, I can go negative 2/3 FAD. It's negative 2 over 3 F. And instead of FAD, I'm going to substitute it in for FAC. So I substitute FAD for FAC, and it's minus 2/3 of FAC plus 1 over root 2 FAB is equal to 0. So now there's only two variables instead of the 3 like before. So what I can do is I can move the two FAC variables to the other side. So I'm going to get 4 over 3 FAC is equal to 1 over root 2 FAB. And what I can do is I can just move that root 2 to the other side. So I can go, therefore, FAB is equal to 4 root 2 over 3 FAC. So now I got FAB in terms of FAC, and I have FAD in terms of FAC. So now I'm going to go dot, dot, dot. This will be equation 5. What I want to do is I want to take equations 4 and 5 and throw them in to equation 3. And the reason why is because everything in the end will be in terms of FAC. So there's only one variable, one unknown. So if I go up here, the first one is 2/3 FAC. And I want everything in terms of FAC, so it's perfect. So we're going to have 2/3 of FAC. And then the second one is 2/3 of FAD. But we know that FAD is actually just equal to FAC. And the final one we have before the 490 is plus 1 over root 2 FAB. So we're going to go plus 1 over root 2. And instead of FAB, what we're going to do is we're going to substitute 4 root 2 over 3 FAC. And we know that this is going to be equal to the 490.5. So I just moved the 490.5 to the other side. We can simplify this even further. And what we're going to get if we add up the 2/3 plus the 2/3 plus everything in those brackets is we're going to get 8 over 3 FAC is equal to 490.5. Well, that's pretty simple. I'm sure you guys can figure this out. So we find that FAC, remember this one's also just straight up equal to FAD. And what we find is that one's equal to 184. And then we got to check the units. It's going to be newtons. And this is part of the answer. So remember, the final goal is to find all those forces in all the cables. Oops, that was terrible. And we just found 2 of the cables right here. Wow, this is not working. You guys have better luck in your midterm than me drawing boxes. Well, that didn't work, but I can make it work. So there we go. So 2 out of the 3 forces. Well, now how do we find the last force? Well, if we go up to equation 5, we can find FAB if we know FAC, which now we do. So we can go FAB, and it's equal to 4 root 2, all divided by 3, of FAC, which is 184. When we substitute that in, we're going to get 347. And this will be newtons. So therefore, FAB is equal to 347 newtons. Alrighty. So we can kind of put a box around that. And if we go up and check, because remember, it's always good to reread the question, make sure that everything's good. What we want to do is determine the magnitude of the force in each of the three cables. And that's exactly what we did. We have FAC, FAD, and FAB all labeled nicely. There's their force. So part A is done, and that was worth a lot of points. That was worth 8 points. So FAB, I got F's in my head. Now we can move on to part B. Now part B is a very interesting question, and they love this on midterms. It's one that a lot of students usually get wrong, even though it's actually a very, very easy question. It says, if the maximum tension, and this is what will get you right here, and this is what you have to look for, maximum. So if the maximum tension of each of the three cables can actually only support 100 newtons, determine the greatest mass in kilograms that the flower pot can be hung on the setup. So basically we're trying to find the mass of that pot so that the maximum force in any of those cables is 100 kilonewtons. And if you look at that, you're thinking, okay, well, that was pain in the ass to find the forces the first time. Why would I want to do that again? So this is what you can do. It's something called elasticity, which means that everything will be exactly proportional. For example, if FAC is equal to 1 and FAD is equal to 2, if I increase FAC to 2, FAD will go to 4. So I multiplied both of those by 2. Everything will increase proportionally. So what I want to do really quick is, how about this? Let's just write down, we have our three forces. We have FAC, FAD, and we have FAB. So in their current state, this is their force. We have 184, 184, and 347. So what this means is all three of these cables would break right now. Nothing would actually happen. So we have to find a way to lower these down to 100. Well, the first thing you're going to have to do is identify which one's the critical one. Which one will have the most force on it? Which one breaks first? And if you look, it's obviously going to be FAB, because the force in FAB is a lot higher than those in FAC and FAD. So what I like to do is I'm going to say, okay, that's my critical one. And then what do I want that to be? Well, I know that the question says we want a maximum of 100. So what we have to do is we have to find a factor that takes us from 347 over to 100. And what we do is, all we're going to do is we're going to take that 100 divided by 347, and what we find is our factor is 0.288. So if we times 347 by 0.288, we actually get 100. So what we're going to do with that factor now is we're going to multiply everything else by that factor to get its proportion. So if I were to multiply the 184 by that factor, I'm going to get 53.0. So these ones are going to be 53. So they're all multiplying by the same factor. So now it's kind of like, okay, well now if we look at our forces in the cable, one of them's 100, which is the maximum what we want. And then the other forces are all lower than 100, which is still okay, because none of them are greater than 100. So this factor must be true. So what we're going to do is we're going to take our mass, which is equal to, we're going to take the 50, which is what it was originally, and we're going to times it by that factor. So 0.288. And what we get when we do that is 14.4. So this is the mass of the flower pot when FAB will hit 100, and at that moment FAC and FAD will be at 53. So it's actually that simple. It's worth 2 marks, but the calculations, as you guys can see, are extremely quick, and you guys can solve it extremely quick. So that's our final answer. So let's just put a nice box around that, letting everybody know this is what I want to mark. So keep in mind elasticity, guys. It'll pay you another visit in the second half of the course when we get to trusses, and that's when it becomes a lot more important. But for now, all you're gonna have to know, everything is proportional. We can just take a factor, multiply everything by that factor, and it all works out fine. So we look up the question, It says if the maximum tension in each of the three cables can actually support 100 newtons, determine the greatest mass. Well, we did that. So the question is solved. And with that, question 2 is solved. So particle equilibrium, guarantee it's going to be on your midterm. Almost always is. Best thing to do, use unit vectors to find the components of the forces. And then from there, you can use systems of equations to solve for the unknowns. And again, if it asks for a maximum, just remember everything is proportional. Everything's proportional. You guys can find the maximum, or even if it's a minimum, very, very simply. So that concludes question 2, and I will see you guys in the next question.